Let's try to solve this problem about ideal Rankine cycle. Consider a steam power plant operating on the simple ideal Rankine cycle. Steam enters the turbine at 3 MPa and 350 degrees Celsius and is condensed in the condenser at a pressure of 75 kPa. Determine the efficiency of this cycle. So to solve ideal Rankine cycle, first draw the schematic diagram of the process. So the steam enters the turbine, and then it leaves the turbine and enters the condenser. After, it goes to the pump, and then it goes to the boiler. Now let's name this as state 1, state 2, state 3, and state 4. So this is the schematic diagram. Then the next step is to draw the TS diagram. This is the S and T. So what most ideal Rankine cycle looks like in ITS diagram is you have the high pressure line here, and it goes down, and then you have the low pressure line here. Then in state 1, it happens here. This is state 1. This is 5 MPa. No, 3 MPa. 3 MPa. And this is at 350 Celsius, and this is state 1. What most ideal Rankine cycle looks like is it goes down. It is an isentropic process, constant entropy. It goes down to state 2 at 1, 2, 3, so at 0.075 MPa. Then, so it goes there. Then it undergoes a constant pressure process. This is state 3. Then it goes another isentropic process. State 3 to state 4 is the pump. Then it goes back to the turbine, which is in state 4 and state 1. It is a constant pressure process. So state 1 to state 2, it goes a constant entropy process. It happens in the turbine. Then state 2 to state 3, it happens in the condenser, which is a constant pressure process. Then state 3 to state 4, a constant entropy process, which happens in the pump. And 4 to 1 is constant pressure process, the boiler. Then to solve for the efficiency is you have this formula, which is equal to work net over Q added or Q in, which is equal to work net is equal to Q in minus Q out. So you have Q in minus Q out over Q in, so which means 1 minus Q out over Q in. And then Q out is equal to enthalpy of 2 minus enthalpy of state 3. So H2 minus H3. And then Q in is equal to Q in happens in the boiler. So H1 minus H4. H1 minus H4. Now heat is equal to enthalpy, it is because it is a constant pressure process. Now, let's start by solving state 1. So, in order to solve the state of a vapor, you need two intensive properties, and we have pressure and temperature. So, we can solve the state. So, at table 3, we know that it is in table 3 because this is in superheated vapor. So we know that this at table 3. So I'm using the green book, the steam tables green book at 3 MPa. At 3 MPa, 3 MPa, 350 degrees Celsius. So 350 degrees Celsius, we can get H1. H1 is equal to 3115.3 kilojoules per kilogram. So now we have H1. So we need 4 enthalpies because there are 4 states. Now, in order to solve state 2, we can get the entropy of state 1. As you can see, the entropy of state 1 is equal to entropy of state 2 because this is an isentropic process. So let's get that. So the same table, S1 is equal to 6.7428. This is in kilojoules per kilogram Kelvin. So let's use blue there. Now, in order to solve state 2, we use table 2. At table 2, and as you can see, it is at 0.075 MPa. So at 0.075 MPa. So let's go to table 2, 0.075 MPa. And we must remember that S2 is equal to S1, which is this. Then we can determine if S2 is wet. If S2 is less than Sg, then S2 is wet. So Sg is equal to at 0.075 MPa 7.4564 kilojoules per kilogram Kelvin. Now, as you can see, S2 is less than Sg. Therefore, wet. You have a wet vapor, you need to solve for x, and you can solve for x by using this formula. S2 is equal to SF plus X SFG. Then we have S2, we have SF by the table, we have SFG by the table. So we can solve for X. So let's go here. X is equal to S2 minus SF over SFG. We have S2 6.7428 minus SF at 0.75, which is 1.2130 over SFG 6.2434, 6.2434, which is equal to, I'm gonna use a calculator here, 6.7428 minus 1.2130 divided by 6.2434. So this is at 0.8857, which is equal to 88.57%. Now that we have x, so we have x. Now that we have x, we can solve for H2, and we can solve for H2 by this formula. H2 is equal to HF plus X HFG, and as you noticed, it looks the same as this formula. So let's plug our numbers here. Looking at the table, at 0.75 MPa, HF is equal to 3384.39 plus our X is 8857, 0.8857, multiplied that to HFG at 0.75, that's 2278.6, and use our calculator. Multiply that to 2278.6 plus 384.39. That's 2402.5535 kilojoules per kilogram. Let's highlight that in red. Now we have H2. Let's go solve for H3. Now to solve for H3, as you can see, they have the same pressure, and H3 is just equal to HF. So at table 2, 0.075 MPa. H3 is equal to HF, which is equal to, at the table, 75 HF 384.39 384.39 kilojoules per kilogram. And let's highlight that. So to solve for H4, you need, let's box this first. So to solve for H4, you need to use this formula. That's H3 plus V3 specific volume times delta P. This is the H4 is approximately equal to this. So let's put that. H3 is 384.39 plus V3, that's VF. V3 is equal to VF at 0.75. So that is equal to 0.0010373. That is in cubic meter per kilogram. Then multiply that to a delta P, but the unit in pressure needs to be in kilopascal, so that your final unit is kilojoules per kilogram. So 3 MPa is equal to 3000 kPa. So minus the change of pressure, the low pressure line is equal to 75 kPa. So 75 kPa, and that is equal to, let's use our calculator. So 0.00010373 times 3000 minus 75, that is 3.034. Then add that to 384.39, that is 387.4241 kilojoules in per kilogram. Let's highlight that in red. Now we already have all the enthalpies. We can solve for the efficiency. Again, enthalpy, thermal efficiency is equal to 1 minus, let's show this, H2 minus H3 over H1 minus H4. So H2 minus H3 over H1 minus H4, H1 minus H4. Then we can substitute the values. H2 is equal to 2402.5535. 2402.5535 minus H3. H3 is here 384.39. 384.39 over H1. H1 is equal to 3115.3. 3115.3 minus H4 here 387.4241. 387.4241 4241, and let's solve. We'll use our calculator. So 2402.5535 minus 384.39 divided by 3115.3 minus 387.4241. 1, subtract the to 1, so the answer is 0.2602, which is equal to 26.02%. And let's use blue. This is the final answer. And that's how you solve an ideal Rankine cycle.